Okay, shall we start? Okay, so the next speaker is Takato Yoshimura from Oxford. And he's going to tell us about ballistic macroscopic fluctuation theory for integrable systems.
Okay, so let me first thank the organizers for kindly giving me an opportunity to give a talk in this wonderful workshop. It's been a great pleasure to take part in this workshop. So what I'm going to talk about today is about how one can generalize the notion of the macroscopic fluctuation theory to study some large deviation-related physics in many-body systems that support first ballistic transport. And what I mean by ballistic transport is quite simple. So if the largest possible scale dynamics in your system is characterized by some other hydrodynamics, then that's what I mean by the ballistic transport. Of course, there could be some corrections to the ballistic transport. For instance, there could be diffusive corrections, which is typical case in integrable systems, whereas in non-integrable Hamiltonian systems, the corrections tend to be super diffusive. But these corrections do not basically play any role in what I'm going to do. And also have to make a brief comment on the macroscopic fluctuation theory before going into the details. So it goes by the name of the MFT. This theory basically was initially devised to study the large deviations in many body systems that support purely diffusive transport. For instance, this simple symmetric exclusion process SEP is characterized by some diffusive hydrodynamics on the large scale. So in that case, you can use this MFT to study the large deviations in the SEP. But so like I said, it was initially meant to be for the purely diffusive transport, but the idea itself seems to be quite universal. And as it turns out, it is quite universal and can be actually readily generalized to other kind of transport types. So the aim of this talk is to really generalize this conventional macroscopic fluctuation theory to study the large deviations in ballistic transport. And in particular, I'm going to focus on integrable systems. But the theory itself is meant to be quite generic and applicable to many-body systems, so long as it's supporting some ballistic transport. All right. Okay. But to set the stage, I'd like to start with some very simple initial condition, which is some product state that consists of two thermal states, each of which is thermalized with respect to some different temperature. And let's imagine that your many-body systems, well, could be quantum, could be classical, that supports ballistic transport is initialized with respect to this initial state. And let's say the system is infinitely extending, so the system size is infinite. In that case, what you would expect is that if you start out with this kind of initial condition, if you wait for a long time, then you'd expect that there would be some kind of emergent persistent current at the junction point where the two subsystems were initially connected. And depending on the available conservation laws, you might see some particle current or the energy current, and etc. So the question now is, how do we characterize these persistent ballistic currents?
Why doesn't the current increase over the
Oh, sorry. Oops. No, it does not. It's a persistent current that is kind of fueled by the asymptotic path. It scales at t, but I mean, if you divide by t and take average, then it's always constant. That's what I mean. Okay. So, I mean, of course, the immediate quantity one can look at is the average current, which is meant to be finite. Of course, if you don't take this average, it's going to be blow up. But this quantity, so J hat here is defined in this way, is, I mean, the average is just the crudest possible kind of quantity one can look at. So in order to see some more intricate information about the fluctuating current, so the current is now fluctuating, one can study, for instance, this kind of object, which is called variance, or even higher cumulants, such as the skewness, or even like fourth cumulant, and etc. And these guys are supposed to contain some information as to how likely some rare event could take place in this system. For instance, what I mean by rare events is that, you know, that, for instance, if you focus on the energy current, for obvious entropic reason, the heat current, I mean, energy current will be flowing from the left to the right. That's entropically favored. But that does not necessarily forbid for the particles to occasionally flow from the right to the left. Some particles are indeed allowed to do it. It's just that it's not as likely as the other way around, meaning the particles falling from the left to the right for the entropic reason, but they can still happen. So these guys, these quantities, cumulants, are expected to encode the information about this kind of fluctuation that is taking place in this system. And these guys are something, I mean, this fluctuation in the system is something I want to understand, also what the MFT allows us to describe. But okay, instead of looking at each cumulant, what one can do is to group them together and then consider some generating function, this guy, whose existence is kind of guaranteed by the large deviation principle for this kind of object probability. So this is a kind of assumption, which is physically a sensible one. So we expect that the large deviation principle for this kind of probability distribution is generically expected. And if it turns out that if that is not the case, then the MFT in general does not really work. Anyhow, so how do we then compute this FM lambda for ballistic mini-body systems? So mini-body systems that support ballistic transport. And I have to stress that this there's actually already a theory that was meant to compute FM lambda for ballistic many-body systems, which was proposed by Benjamin and his collaborators a few years ago. But the point here is that it works only for the homogeneous initial condition. So starting with some Gibbs ensemble, or could be generalized Gibbs ensemble if you're dealing with an integrable system, which means that so this theory that goes by the name of the ballistic fluctuation theory, BFT, does not quite work for this kind of inhomogeneous initial condition. So this kind of motivates us that to get some kind of universal theory that allows us to really describe the large deviation of the system in a simple unified manner. And that's precisely the MFT is able to do. So, and although the idea of MFT was briefly introduced in the Benjamin's talk, I'm going to explain a bit the background of it and also say a bit more about it before going into the application of it to the integral systems. All right. So the power and the beauty of the MFT is that you don't have to really know anything at all about the microscopic dynamics of the system for the MFT to work. So only inputs needed for the MFT is some hydrodynamic inputs, let's say diffusion constants or some transport coefficients. So stating another way, if you know the hydrodynamics of the system, then you can do the MFT for the system to understand the large deviations of the system. So for simplicity, let's consider some many-body system, could be quantum, could be classical, with N conservation laws, which support ballistic transport. I mean, if I mean that by saying N conservation laws, it's kind of implicitly meaning that ballistic transport should be there, but anyway. Right. So, but to do a hydrodynamics, you cannot really choose arbitrary initial conditions you like. It has to start with some particular class of initial conditions, which are the local equilibriums. For instance, local Gibson symbols, or it could be local generalized Gibson symbols, which are given by this kind of statistical average, where the inhomogeneity is encoded through these Lagrange multipliers with the parameter small l, which is supposed to be sent to infinity later on. So this is the class of initial conditions that I have in mind. And what hydrodynamics tells you is that if you start out with this kind of initial condition, the microscopic dynamics will not really agitate this local equilibrium and let the form of it remain intact throughout the dynamics. Which means that this local equilibrium will propagate in a stable way. So that's the basically idea of order hydrodynamics, as simple as that, but one has to implement this idea in terms of equations. So what hydrodynamics allows us to do is, for instance, to evaluate some large-scale equation functions for the average of some local observables. But much easier to start with already coarse-grained mesoscopic observables, in order to wash out some non-Eulerian kind of behavior in the observables. So given this local observable, we define its coarse-grained version like this, meaning that this observable is space-time averaged over this kind of space-time region that we call Hood cell, whose size is now written by Lagia. And the point here is that this L, the size of the cell, is supposed to be very large compared to the microscopic scale of the system, such as interparticle length, so that there are enough number of particles inside of the cell. But still, it's meant to be small compared to the macroscopic scale, say the scale that is entering here. So that if you take the small L infinity limit, then basically this full cell shrinks to the point. So this kind of separation of scales is expected to take place. And now, what the order hydrodynamics allow us to obtain is, for instance, this kind of behavior. I mean, the basic space-time average of the mesoscopic observables. And this is now simply given by some equilibrium average, where the space-time dependence is now coming from these Lagrange multipliers. And note that this x and t in the Lagrange multipliers are now meant to be macroscopic, because on the left-hand side of it, it's already macroscopic space-time. So this is quite a simplification. And one can also recast it in terms of the function of the charge density averages, because you see, if you put this charge density in the trace, and you can see that the number of the charge density average is basically as many as the betas. So there should be some kind of bijection between the set of the betas and set of Qs, I mean, charge density averages. So this means that we can rewrite this average, equilibrium average, parameterized by beta, in terms of some functional of Qs, the charge density averages. So this is what I mean by the local relaxation of the averages. Namely, as far as the average is concerned, some microscopic degrees of freedom do not really play any role. And only relevant degrees of freedom are those that are protected by the conservation laws. So this is a kind of message, an important message from the hydrodynamics that also inspires us to go further when we do the MFT. All right. So having this local relaxation of averages in mind, one can apply that to, say, current operator. And now we see that these hydrodynamic equations are closed and can be written in terms of the density averages only, where this matrix A is defined in this simple way, which is just the derivative of J with respect to Q. And also it can be further rewritten in terms of the susceptibility matrix defined in this way. All right, but there is also another way to write the hydrodynamic equation in terms of the betas here, which is again can be directly obtained from this original hydrodynamic equation by using this relation between the beta and Q and the susceptibility matrix. So it's just a matter of rewriting. And as it turns out, this is a kind of more convenient version of the hydrodynamic equations when doing the MFT. So as I have been explaining and emphasizing, hydro is really all about that, about the dynamics of the averages and equilibrium correlation functions obtained out of them. But in order to access the quantities that are strongly affected by the rare fluctuations, one also has to know how the fluctuations propagate in time, or said in another way, according to what kind of measure the space-time profile of the charges are going to fluctuate. And this is a kind of important input in the MFT. But to understand that, we have to start with characterizing the initial fluctuations. So to that end, let us start with defining the mesoscopic variables, fluctuating mesoscopic variables in this way. So this is meant to be fluctuating, and because this is before taking some kind of average. And now these fluctuating mesoscopic variables are, the average or the correlation functions of them are expected to be obtained by this measure, where e to the minus L f of Q is nothing else than the density relativization function. Or alternatively, one can say that this is the probability of observing the density profile Q1x and 0, given some initial background density Q ini. And it's a simple matter to write down this exact expression for the f. I don't bore you with its derivation, it's just given simply like this, where the beta ini is a Lagrange multiplier is associated to the background density Q ini. And also here this S is an entropy, entropy density. In the integrable case, this is nothing else than the Yang entropy density. So this is the kind of formula one has to use to evaluate the correlations that involve this kind of mesoscopic variables. Now, the question is, how do we generalize this measure for the initial fluctuation to the measure for the space-time dependent charges? Okay, here comes the most important assumption we make, which is that the local relaxation of the fluctuations. This assumption is, this is going to be the only assumption we are going to make. And this basically tells us that mesoscopic means of the local observables, this guy, do not fluctuate independently, which could be a bit counterintuitive, but still they do not fluctuate independently, but are fixed functionals of conserved quantities in this way. So of course, this is strongly inspired by the notion of local relaxation of the averages. But the important point here is that the function form of O, so this function form is not fluctuating. What is fluctuating here is the only densities. This is has to be emphasized. The function form of this O is yet to be determined. So how do we do that? Well, one can take, for instance, time equals 0, like this, and invoke that this path integral formula that is valid at time equals 0. And I have already replaced this O with this O of Q because of this ansatz. You just plug t equals 0 in here, and then you get this. And this is now I mean, you can evaluate this path integral because everything inside of the path integral is now a functional of the Q's. So you can perform exactly the computation. And if you do that, one can fix the functional form of this O to like this, where this O, so it's a bit hard to distinguish the different fonts, but this is, in terms of LaTeX, this is math TT, the functional form of the average of the O. So this is quite a good news. Now we can have two notions, separate notions that are closely related to each other for the average and the bare fluctuating variables. The one is local relaxation, the averages. This is coming from hydrodynamics, so one can take it kind of for granted. Whereas this local relaxation and the fluctuations is new. This is the assumption we have to make somewhat, so both of which are expected to be valid for L to the infinity. And you might think that this is not really a well-grounded assumption. But if you recall that, the fluctuations that we are looking at are not the arbitrary fluctuations. We care only about the fluctuations pertaining to the Euler dynamics or Euler scale, if you like. And in that case, as one can infer from the local relaxation averages, only degrees of freedom that are contributing to the Euler scale are those that are protected by the conservation laws. So in that sense, it's not so outrageous to assume that this kind of local relaxation of fluctuations. But still, this is a relatively big leap compared to this one. So, but anyhow, this is what we are going to use. And once you are happy with this local relaxation, the fluctuations, then one can apply that to the current, a fluctuating current like this, which is now fluctuating only through the Q, this guy, and write down the measure for the space-time dependent Qs, fluctuating Qs, which reads like this in a very simple way. This looks more or less similar to what I have written already for the initial measure, except this continuity equations, which is now put in there in order to enforce the continuity equation. And furthermore, this the current, the fluctuating current, is replaced by this Q-dependent current, which is a cos-inverse of the local relaxation of fluctuations. So this is the ansatz, BMFT ansatz that we are going to use. And with this measure, one can evaluate the BMFT average for arbitrary observables, presumably, in this way, and which we are going to identify with the local equilibrium average. And if you know a bit about conventional MFT already, you might wonder what would be the relation between this MFT ansatz and the one that is often used in the conventional diffusive MFT. Well, there is a clear analogy, obviously, because in the conventional MFT ansatz, the diffusive ones, one usually uses this kind of measure for the space-time dependent density, where the current is now allowed to fluctuate in its own way, but the fluctuation is coming from the noise. So said in another way, it's what is imposed in the continuity equation is nothing else than the linear fluctuating hydrodynamics. So the idea is actually exactly the same, meaning that the current is the fluctuating current has to fluctuate according to the hydrodynamics that is involved in the scale you're looking at. In the conventional MFT case, that's precisely the diffusive case. So it has to fluctuate according to the diffusive hydrodynamics, which is the linear fluctuating hydrodynamics with noise. But if you change the scale you're looking at, or transport types, you have to use the according hydrodynamic equations that are that describe the dynamics at that scale, which is in the ballistic case nothing else than the Euler hydrodynamics. So you just use that idea to write down this one. So actually, one can start from this conventional MFT ansatz and infer that kind of idea, and then immediately write down this kind of measure for the density, space-time dependent density. But we thought it's kind of nicer to start with kind of bigger picture, which is the local relaxation of fluctuations. And I think this is actually what is underlying in this BMFT. But the point to be emphasized is that this is a bit of overkill, as far as the application of the MFT to study the current fluctuations, for instance, is concerned, because only things you have to do is to assume this kind of form for the current, not for the arbitrary observables, but still. One can make an ansatz that the local relaxation of the fluctuations is taking place. Anyhow, so this is the formula I'm going to use. Okay. And in particular, I want to evaluate two kinds of objects. The first one is the order scale dynamic equation functions, defined in this way. And other one is the scaled cumulant generating function, defined in this way. And note that this okay, I'm choosing some particular conservation laws, I star, for the scaled generating function. Could be density, could be energy. I mean, it's up to you. And it has to be, the time has to be rescaled by LT. Otherwise, you don't see some non-trivial, you don't see the effect of non-trivial inhomogeneity of the background. So you've got to rescale in this way and divide by 1 over LT. And that's the scaled generating function we want to evaluate for the inhomogeneous initial condition. Of course, if the initial condition is homogeneous, then you don't have to put these large parameter in here. All right. So these guys.
That is that your microphone is on. This create the microphone of your computer should be off because it could create some echo in the video.
Oh, okay, that's me.
Sorry for interrupting.
No, it's okay.
That's on audio.
Yes.
Down.
No, this is.
No, the thing is, I can't see this bit from my side. So
That what you see is something different because he's on the phone.
can you actually control that from? No, I cannot touch these bits.
Poi non si sente il suo microfono.
How can you do that?
Because there's somewhere a microphone here. But
It's zero.
it was already.
No, but this is speaker, not microphone. Perhaps I should stop sharing.
No. Then where is your Zoom? Is this one? May I click?
So someone complained that
the technician noticed that the audio is bad.
okay.
Maybe this
I think now you can mute it.
Yes.
Good. Perfect. Okay. Thank you. No. Thank you. Okay. So better now. Good to know. Thank you. When these quantities can be evaluated by the BMFT as we expected, and you just have to plug these mesoscopic fluctuating variable inside of this path integral, and then you perform the path integral, and in principle, one can work that out and obtain these quantities. And that's precisely what I'm going to do for the ballistic transport, ballistic many-body systems. Okay, I mean, these double brackets are there just to emphasize that these are different from the local equilibrium, but because these are, path integral for the fluctuating, presumably classical variables. But anyway, we identified this with the local equilibrium average. Okay, so now we are in business. So having this path integral formula, what one can do is to, for instance, okay, let's start with the current fluctuations. You plug this guy in here, and you kind of regroup everything. And after exponentiating this delta function, by introducing the auxiliary variable h, you realize that one can write this path integral formula with the MFT action in this way. And actually, you don't have to even work out this path integral. If you take the large small L limit, then it's obvious that this path integral is dominated by its saddle point. So you just have to know what kind of configurations would contribute to the saddle point. So the problem now boils down to the evaluation, basically the optimization problem of this action, which amounts to solving these following MFT equations like this. Sorry, this is just step function. So this is what we've got to evaluate, to solve. And then once you do that, you just plug the optimal profile of the beta and h in here, and then evaluate this path integral. That's what you've got to do. And okay, so just to emphasize that these betas are kind of variables that are conjugate to the Q. So these are basically equivalent to the Qs. For just for convenience, I'm writing the MFT equations in terms of the betas and the H, but I could also write these in terms of the Qs and the H. This is just a matter of convenience. It's not physical. Okay, so theta is a step function, heaviside step. Yes. Okay. Yeah. Right. Yeah, this theta is coming from basically the fact that current can be written as the difference of the densities, and the same old thing. Right, but as it turns out, it's not as easy as I said. The solving this kind of MFT equations is quite tricky because this nonlinear term generically amounts to some kind of sharp structure that we often call shocks. And basically, there's no guiding principle to single out the weak solutions. So unlike in the hydrodynamic case, where you can resort to something like entropic conditions. So it's a bit tricky. And what one can do sometimes instead is to start with some regularized version of the system. Say, in the case of the TASEP, there is a kind of regularized version of this model called the WASEP, weakly asymmetric simple exclusion process, and do the MFT for that and take the totally asymmetric limit. And this was done by, for instance, the paper by Bodino and Derrida. Although this equation looks relatively simple, it's could be tricky. But good news is that as far as integral systems are concerned, we don't have to worry about that kind of subtlety because it's been known that there's no shock in integral systems. So one can just solve these MFT equations and then do the analysis. All right, and as I anticipated, I don't think I have time to talk about this, so I just made a brief comments. But actually, the structure of the MFT equations implies the Galopotti-Cohen type of fluctuation theorem. And this is this kind of symmetry. So this theorem basically tells you that if you start out with this kind of initial condition, the step initial condition, the scaled cumulative generating function would satisfy this kind of symmetry relation, which is quite non-trivial. All right, but the claim of this, what one can learn from the MFT equation is that already at the level of the QIs, so these optimized density fields, some kind of symmetry that is reminiscent of this fluctuation theorem is already encoded. So from the symmetry of the density optimal density profiles, one can actually get this kind of symmetry relation for the scaled cumulative generating function. But anyhow, that's one can get out of the MFT equations without having to deal with each microscopic, each different model. Right. But now another intriguing observation can be made by looking at instead dynamical correlation functions, and in particular 2-point functions. So this guy is again to remind you, they divide in this way. right? So involving two macroscopic variables and they're rescaled by L. That's the kind of order scale dynamical correlation functions. And this guy can be evaluated in this way, again, through the path integral, where this action is now written like this. And I'm just going to go quickly, but you can eventually simplify the situation. And in the end, at the end of the day, the evaluation of this order scale correlation function boils down to this kind of simple evaluation of the densities with respect to lambda and set lambda to 0. But the profile of the density has to be obtained by solving the MFT equations again. So once you do that, you in here and then do this term, lambda derivative and get this action. Formally, one can do it. And surprisingly, what you get is that this kind of statement, I mean, this order scale correlation function has not only the local equilibrium weight, which is usually what you expect, but also some long range correlations. This is quite surprising. This basically tells you that even if there's no initial long range correlations, they could themselves build up throughout the dynamics, and then eventually amounts to the correlations amongst the fluid cell. This is, at least to us, quite surprising because this isn't really the assumption one usually makes. I mean, we usually assume that fluid cells are always uncorrelated at any time slice. But this MFT tells us that that is too naive. All right, so setting another way, local equilibrium is true for only averages. And once you talk about correlation functions, that's not quite true. So you cannot quite use this kind of expression for the higher point correlation functions. Okay, and one can also see that this kind of long-range correlations could develop because of the coupling between the normal modes on some inhomogeneous background. So there are three conditions one has to satisfy in order for to see some long-range correlations. One is multiple conservation laws, meaning that if the system has only one conservation law, like TASEP, you don't see this kind of long-range correlations. Another one is that the interaction. So the system has to be interacting, cannot be like free fermion. And thirdly, you have to also have initial inhomogeneity. So the situation is like this. So at some time, the two normal modes are excited and they kind of propagate in the space-time with different velocities. But because of the interaction and the initial inhomogeneity, they retain the memory of the inhomogeneity and they keep kind of correlated even after having traveled for a long time and long distance. So that's the kind of idea, which is actually, I think, as far as we know, there is only one paper that noticed this kind of mechanism in the context of fluctuating hydrodynamics. But even in this paper, they didn't really imagine that this really holds in generality. They focused on a very specific kind of initial condition. So what the ballistic MFT, BMFT, allows us to, implies is that this kind of long-range correlations are quite ubiquitous in many body systems that support ballistic transport. And this is a bit different from what the long-range correlations that were observed in a different context, for instance, in the NES, in the partition protocol, because these long-range correlations are basically decaying like 1 over x squared, and so they originate from a different mechanism, which is the non-locality of the NES density operator. So it's a bit different thing. All right, so I'm going to, having formulated the BMFT for the ballistic transport in general, I'm going to apply that to integrable systems. Oh, I have. No. Sorry. So I think many people talked about the integral system already. So let me just go quickly. So so GHD is a hydrodynamic theory for integral systems, and it's quite universal because basically on the large scale, all the integral systems behave like pretty much the same. and pretty much like the tracer particles of the hadrons. So in a sense, they on the large scale, all the integrable systems behave like hadrons with a velocity-dependent phase shift, if you like. All right, that's why GHD equation is so universal. Using the technology of the TBA, thermodynamic ansatz, one can rewrite the hydrodynamic equation like this. And as it turns out, it's easier to rewrite this in terms of this one, which is basically the same hydrodynamic equation that I used in the previous slides, except that now the labeling is replaced by the quasi-momentum instead of the integer label that labeled the each conservation law. But this is to be understood as like vector and matrices and all that. And also to do the computation, it's easier to transform the hydro equation into the normal mode hydrodynamic equation, where the epsilon is something called the pseudo energy, and obtained by this kind of relation, where the R is the matrix that diagonalizes the flux Jacobian. And also in terms of TBA quantities, they can be written like this, where N is the usual distribution function, whereas the T is the differential scattering kernel. All right. So, and also, yeah, just to emphasize that this rho of theta is the density of the quasi-particle, whereas the VF is the velocity of the quasi-particle. I mean, something like the average of the velocity after having traveled for a long time and long distance. Okay, so it's quite clear that I don't have time to go through the method of characteristics for the GHD, but it's not really needed. So let's quickly skip. Now the MFT equations. So let's focus on the current fluctuations in integral systems. And the MFT equations are basically like this, which look pretty similar to the usual non-integrable case. Again, except these labelings are now replaced by the quasi-momentum. And also here, the H theta is nothing else than the one particle eigenvalue of the conserved charge Qy. All right, and now to solve this MFT equation, one has to go to the normal mode, epsilon, in this way. And motivated by this, one can also introduce normal mode associated to the H, which we called G. And G can exist because of this kind of a consistency relation. So this is good because now using this normal mode representation, one can, so these guys are basically the rewriting of the MFT equations for the G. And this can be solved very easily by the method of characteristics. So G of X and T is written like this, where R is some quantity coming from the method of characteristics, and it's not really important here. And using this, because we know the profile of the G theta at X and T, from this one, you plugged R theta of X and T in there, and then you get this kind of equation. All right. So having this, plugging this back to the MFT equation, one can reduce the MFT equation to just the simple GHD equation with the lambda dependent initial condition. So this looks a bit monstrous, but one can still work that out. Anyhow, this is so once you solve it, you can evaluate this guy and get this scaled congenerative function. For instance, but that being said, it's in general a bit hard to directly compute f from lambda. So what one can do instead is compute the lower cumulants, like second or third cumulants, and we did it for the homogeneous initial condition, for instance, and they agree perfectly with the results obtained by the ballistic fluctuation theory, which were also confirmed from the numerics. So everything is consistent. But the power of the VMT is that one can rather easily extend this to the inhomogeneous case, including the partition protocol. And for instance, we computed C2, the second cumulant, like this. And it turns out that this is given in a simple way, and it's fully fixed by the nest at xi equals 0. And indeed, this matches pretty nicely with the numerics. And so this numerics is done for the hard rod simulations. The hard rod is a very simple system. It's just made of a bunch of hard rods, and Hamiltonian is given in this way. So it is an integrable system, one of the prototypical integrable system that is classical. And also to the station value is controlled by the diffusive correction. Now, what is more interesting is that the dynamic correlation functions. One can repeat exactly the same thing that I talked about in the non-integrable case, I mean the usual case, by simply replacing the labels to the causal momentum. And yeah, I will just skip all these. Eventually, one can reduce the problem into this kind of GHD equation, and one can calculate long-range correlations. And this is not meant to be instructive or anything. It's just that even though in the integral case, one can calculate things quite precisely, one still has to go through sometimes pretty nasty evaluations. You have to solve these consistently and then plug this, for example, Carly E to this expression. You can't quite see it clearly, sorry. But, and then finally obtain this E, I, Y, and I2. Anyhow, the point here is that you can still do it by numerically writing this quantity. But the result is quite mesmerizing, because if you compare this result, which looks somewhat monstrous, with the numerics, hard rod simulations, for some simple protocol, Bumpery's protocol with the two velocities, one sees that, for instance, this Euler scale correlation function on the time sliced at t equals 0.5, the agreement is quite nice, and all the points are within the error bars. Now, and also one can also look at this symmetric version of the Euler scale correlation function, like this, and the agreement is again super nice. So, and this is quite nice because despite of these small numbers, I mean, these are quite small, but still they are agreeing pretty well. So this is quite convincing that, and allows us to be confident about the this BMFT. And one can also see that by increasing the full cell size, sorry, not full cell size, the size of the inhomogeneity, these data basically collapse onto the same value. So there is a convergence of the scaling. Okay. All right. So yeah, just quickly go through the conclusions. So as I introduced, the BMFT is quite a powerful tool to study not only the current fluctuations, but the dynamical correlation functions on a large scale, Euler scale in your case. And it gives us a really unified method to address all these. And the only one underlying principle / assumption in the BMFT is that the local relaxation of the fluctuations. And having this for granted, one can work out all these computations. And it works particularly well with integral systems. But a natural question next is to how to verify this BMFT for non-integrable systems, presumably some physically interesting model like harmonic chain or some other models that are relatively simple, say AHR model, which is a bit like a two-component generalization of TASEP or ASEP. And also in this simple case, one can even try to microscopically calculate these quantities that I looked at and verify the predictions from the BMFT. And one can also consider some corrections to the BMFT, and maybe one can also look at the effect of quantum fluctuation instead of thermal fluctuation, but these are a bit hazy. So yeah, we have to make things a bit more clear. Anyhow, thank you for the attention.
Okay, thanks a lot for your talk. Are there questions? Okay, maybe let's start with one. So from what I understand, the reason for finite correlations in the MFT is due to the nonlinearity in the current. But
yes, nonlinear current, meaning that there is an interaction. Yes.
But in TASEP also current is nonlinear function of density, right?
Yeah, but as I explained, there are three conditions to be satisfied. The first one is, as you said, interaction, but another one is the multiple conservation laws. And that is not true in the tacit case.
And how do you see it? How do you see that multiple conservation law are necessary? Because
this correlation is coming from the correlation between the normal modes. If there is only one normal mode, there's no way that it can correlate with other normal modes. It has to be the correlation amongst normal modes.
okay, okay.
This is a maybe naive question, but in the usual MFT, I would expect there are fluctuations coming from the initial state, and then there is fluctuation coming from the evolution. So here you just drop the evolution because
that's
there
a
is
good
no
question. Indeed, thanks for asking that. So initial condition is indeed taken care in this BMFT because that's the only source of the fluctuation. But the reason why there is no, the reason why we don't have to consider the fluctuation from the dynamics is because it's subleading. It's the fluctuation. I mean, we are looking at the order scale, whereas this fluctuation you're talking about is subleading. It's to do with the diffusion, which is subleading compared to the order scale. So that's why we can forget about it in this case. But in general, yes, that's always present.
Other questions?
Question is, what do you learn from this analysis on the anomalous transport problem for anharmonic chains, if anything?
Well, I'm not sure what we can learn really, but at least what I was saying that there is a prediction that generically we would expect to see some kind of long-range correlation so long as the system supports ballistic transport, which is also the case for the anharmonic chain. So, I mean, it's a, oh, sorry. Okay, anyway, it's natural that, I mean, it's just to check that if the BMFT prediction is true for non-integrable systems. I mean, so far we checked that for the integrable systems, but I mean, presumably this should also be true for the anharmonic chain. So just for the consistency check. It's not like, I'm not sure what we can really learn new from applying the BMFT to the anharmonic chain, but yeah.
Other questions? So can you clarify a bit the plot there, the last plot?
Yeah.
No. I mean, just the previous slide.
I think I should. The previous slide, right?
Yes. So what are you plotting here exactly? Because it's not.
So as I said, this is the order scale correlation function, which is defined. It's a 2-point function, density. Sorry, I had forgotten to say that this is a density correlation function, particle density, which is defined. How was that? Here. So defined in this way, and there is scaled by the L. Inhomogeneity. Of course, this value of the small l is kind of arbitrary. So we check that if the data we get is indeed going to collapse onto the single value, and it does. So this is just a plot from the one particular choice of the L, but you can vary L to like, change to say L equals 500 or 100 and see the data is still consistent. But anyway, that's what we are collocating, the density correlation function on the order scale. After there's a rescaling on the time t equals 0.5, so 1/2. And one of the position is set to 0. Whereas this one is a symmetric correlator in the sense that the space is symmetric x and minus x.
But why doesn't decay to 0 large x?
I'm sorry?
Why doesn't decay to 0 large x?
It does. It's just that you don't see it in this window if you take it with x. Yeah.
Oh, okay. If there are no other questions, let's thank the speaker again.